A continuous coastal barrier rises from surf and spray to blunt a moving wall of water. The ground shifts beneath it, joints must lock against uplift and backwash, and a single misaligned seam can become a pry bar for the sea. Engineers refine profiles and wave tank tests, then stack interlocking armor to shred energy at the toe. We'll show the exact build order and the quiet detailing trick that makes discrete segments behave like one machine. Plainly put, the wall's job is to slow and dissipate tsunami energy at the shore, buy inland evacuation time, and shield critical coastal facilities. Coastal residents, emergency managers, operators, and builders depend on it lasting in salt, sun, and seismic shaking. Hazard maps classify this coast as high seismic/tsunami risk. For example, USGS, National Disaster Agency Assessments. The design brief assumes an extreme offshore rupture scenario drawn from government post-event reports and probabilistic studies. With a program reported in the multi-billion-dollar range in planning documents, schedule and quality scrutiny are intense. Failure looks like uncontrolled overtopping, tow scour, and seepage paths that turn a barrier into a channel. Next, how the ground under the wall decides whether it stands or slides. This shoreline is a patchwork of headlands, river mouths, reclaimed flats, and migrating beaches. Teams build a ground model from borings and cores, cone penetration tests, CPTs, grain size profiles, and tide/surge histories. Typical practice adds settlement plates and pore pressure transducers to watch liquefaction and scour risk. See USACE Coastal Engineering Manual, JGS Guidelines. Where weak, saturated sands dominate, crews pre-treat the base with piles, crushed stone blankets, and compacted lifts before any wall takes shape. In other reaches, deep excavations create safe, dewatered pits to reach competent strata. Read the ground wrong and differential settlement or seepage opens paths beneath the wall. The consequence is concrete. In many reaches, this meant piles and graded stone filters before a tide base could rise. Design logic, the system diagram in words. Think in subsystems: 1. Foundations and ground treatment. 2. The wall body. 3. Energy dissipating armor. 4. Port/river gates. 5. Drainage. 6. Access and monitoring. Standard coastal engineering workflow, for example USACECEM, uses wave tank and scale model testing to tune wall height, slope, and toe geometry to overtopping targets. Armor at the sea-facing toe fractures wave fronts and shields against scour. Sloped or stepped faces temper run-up landward. Navigation can't stop, so movable gates knit into the line. Governing principles: watertight interfaces, energy dissipation at toe and face, and inspectable details for decades. The most failure-prone interface is at segment transitions. We'll show the joint detailing that stops leakage and uplift. Before concrete, crews build the job to build the wall. Temporary haul roads and staging yards stitch together fragmented shoreline access. Shoreline work pads let cranes reach the intertidal safely. In tidal reaches and river mouths, temporary barriers and dewatering create dry work envelopes. Material flow splits, aggregates by truck where roads allow. Oversized armor by barge where headlands and inlets choke access. Short tidal windows, hours per day, drive shift work and repeatable task packages. With access in, the real decision point is how loads are tied to the ground and kept there when the sea pulls back. Foundation/anchoring/ground improvement. Where soils are weak or cyclically loaded by waves and shaking, the build sequences pile installation, a draining stone blanket, and a tide base slab to stiffen, anchor, and relieve pressure. In soft deposits, excavation descends to competent strata inside supported, dewatered pits. Reinforcement and forms lock a base slab into that layer. Key risks are settlement opening joints, toe scour, uplift from trapped pore pressure, and seepage bypassing the barrier. Mitigations include deeper toe embedment, graded filter layers, and tying segments back into treated ground or piles. Capacity testing and instrumentation. Typical practice includes static load tests and/or PDA per standards. Confirm piles and treated ground meet design. Design references for tsunami/coastal works. Note significant embedment and excavation to reach bearing layers. For example, Japan MLIT Technical Guidelines. USA CECEM. Get this wrong, and nothing above will stay aligned. Set out. Surveyors pin the control line, elevations, and tow embedment targets. Crews install formwork anchors above the tide line and mark drainage penetrations. Then, fabricate. Reinforcement cages are tied, corrosion cover checked, and embedded parts for joints and drains staged for rapid placement. Place concrete pours run in controlled length segments to manage heat and shrinkage. Finish and curing are timed against tides and temperature. Connect. Expansion and settlement joints go in. Landward drains and relief paths keep rainfall from pressurizing the wall during events. Armor. Cranes. Place interlocking energy dissipating units around the sea-facing toe to protect against scour and fracture incoming waves. Throughout, top-of-wall elevation, toe embedment, and joint alignment must hit tight tolerances, hand width or less, or overtopping and leakage risks wike. Tempo comes from parallel fronts. One segment forms, another pours, a third armors, keeping plants, cranes, and trucks moving. Do this cycle right, and the line behaves like one machine. Get it wrong, and backwash pries the joints. Signature operation, the impossible moment. Divers fan silt from housings and confirm hinges, hydraulics, and ceiling faces are clean and within tolerance. In the control room, operators arm a bottom-up rising gate, one common approach. Pumps pressurize cylinders. The panel lifts from the seabed on guides as position sensors stream back readings. At preset pressure and movement hold points, crews pause to verify deflection and drift under current and swell. Closure brings interlocking edges to concrete abutments. Compression bars load the seals evenly while leak indicators are watched. If differential head or vibration exceeds limits, operators stop, partially reopen to equalize, and flush sediments. Corrosion-resistant steels, sealed hinges, and marine coatings fight grit and salt between rare activations. One clean motion under live water decides whether the harbor mouth can shut on command. Manufacture versus local production. Specialized gates and hardware are fabricated off-site. Soils and concrete are produced close to work fronts where possible, standard mega-project practice. Sea versus road, oversized armor and long reaches move by barge. Constrained headlands force night road convoys in smaller pieces. Stockpile versus just-in-time. Durable items like armor are staged. Perishable concrete inputs arrive JIT to control waste. This is a machine with its own supply train. Next, how safety and quality gates slow or speed that train and make the defense credible. Safety, quality, and verification gates. Quality gates are procedural: test, hold, fix, retest. Concrete is checked with fresh state tests, cores, and cover meter scans against chloride intrusion risks. Steelwork and gate hardware undergo coatings inspections and non-destructive testing. Hydraulics are pressure tested before operation. Survey checks confirm alignment and elevation before forms move. Armor placement is verified for interlock and toe depth. Traceability runs through digital tags and batch numbers per QA plans and typical ISO/ASTM frameworks. Microcase. Honeycombing at a cold joint is caught at stripping, repaired, and re-inspected before it can become a seepage path. Verified parts still need power, controls, and people to operate under stress. Systems integration, controls/operations. A typical operating model links local stations to a central watch. Power and hydraulics drive gates. Communications carry commands. Sensors track tide, vibration, and position against thresholds. Redundancy preserves function. Backup power and manual overrides keep closure possible if an actuator stalls or mains fail. Fire/life safety analogs apply. Isolation valves, lockouts, and safe-to-approach zones let crews service one unit without risking others. Next comes commissioning and drills, proving it works under load. Commissioning, testing, and first-run commissioning. Steps from parts to the whole. Hydraulic and seal checkouts, single gate closures, then coordinated drills across multiple reaches. Instrumentation watches pressures, movements, and leakage during controlled closures. Thresholds trigger holds, adjustments, or rollback. Simulations and physical tests suggest meaningful force reduction and extra evacuation time in many scenarios. While planners stress it is not an absolute shield, a coordinated closure passes when leakage is within measured tolerance and movements track predictions. Payoff: a supervised, milestone closure, and a sober admission that vigilance and upkeep are the price of protection. Environmental constraints, turbidity, noise, habitat disturbance, are managed with typical mitigations: silt curtains, timing windows, monitoring. Dust, traffic, and port access are coordinated so fishing, shipping, and commuting continue. Public safety uses exclusion zones, signage, and shoreline detours. The wall's value is realized through drills, maintenance, and clear public communication.